Hello friends, the topic for this session is consensus. In this session, we will talk a bit about generic consensus and what it means in distributed systems. We will try to understand consensus from the perspective of blockchains, and then we will try to understand consensus from an implementation standpoint, where we'll try to see some consensus mechanisms like raft and proof of work and proof of stake and a couple of others. This session is partially conceptual, where we'll try to understand the relevance of consensus as a concept, and then it's also partly practical, where we look at how consensus is implemented in some of the systems that require distributed computing and what are some of the libraries that implement popular consensus mechanisms. One of the things that we need to understand about consensus from a distributed computing and computing in general standpoint is that it's a problem that's bigger than blockchains, and also consensus has been an area of study much prior to the advent of blockchains. The reason why we have to study consensus as a part of blockchains is because a typical blockchain is a distributed system. It's got multiple different components called nodes that work together to achieve what a blockchain intends to do, which is to provide a trusted ledger system. So with that background in mind, the first thing that one has to do is to understand the fundamental problem of consensus in distributed computing. The reason why it is important to understand why consensus is needed and why we are even talking about consensus is because systems like blockchain, or in general distributed systems, are multi-agent systems, or they've got systems or they've got components that are distributed over a very wide network. In our past session, we have studied distributed computing and distributed systems in a slight amount of detail. So we understand that a blockchain consists of these distributed components that work together to achieve or to provide a blockchain like ledger system. Now, in such an overall distributed environment, one of the things that the system has to contend with is the overall reliability. There are a number of processes that work together to provide that complete set of promises that a distributed ledger has to set up, and as a part of this whole system working together, these faulty processes or these errors or these exceptional situations need to be handled. This often requires coordinating processes to reach what is called a consensus, or in a more generic sense, to agree on some data value that's needed in computation. When we talk about blockchains, this data value could be how much bitcoins does a certain address have after a certain block is committed. So we need to understand this consensus and why it's important, and at what point does it come into play when we are looking at systems like blockchains. One of the ways in which we look at a distributed blockchain is these different instances of a single ledger that exists remotely and are coordinating with each other. And one of the ways in which that coordination has to happen is through an agreement that is to be reached. And this process of reaching that agreement is called consensus. A formal definition is that a consensus is an algorithm or a set of steps or procedure through which all different nodes or peers of a blockchain network reach a common agreement. And that common agreement is about what is the state of the ledger, what is the latest transaction, which block are we at. And this consensus is as a process requiring us to reach that agreement for all of these different elements of the ledger, and it also has to contend with failure of one or more instances of the ledger during that coordination process. So blockchains or any other distributed system work with reliable and unreliable parts, where some components can go offline or be disconnected for certain amount of time or longer durations from the blockchain, in which case we don't get any inputs from those components. So the problem of consensus is, number one, to get everyone to agree upon a certain state, and number two, to also be tolerant of failures of parts of that system. Now, fault tolerance is something that we will separately study as a part of how blockchains operate, but purely from a generic consensus standpoint, we should be aware of how faults occur and how does a typical consensus mechanism address them. As stated earlier, consensus problem is a more fundamental one than just what happens in blockchains. And one of the approaches to generating a consensus is, let's say, for all processes to agree upon a majority value. In this context, a majority requires at least half of the network agreeing upon a certain value through a voting process, and then the rest of the network considering it to be correct and true. So that's one simple mechanism, or in more formal terms, that's one protocol which allows us to reach that consensus. There are hosts of other protocols that take care of different situations of failure and different situations of non-connectivity and a specific type of failure called Byzantine failure. But the simplest one could be the majority one. Obviously, it's too trivial to implement. It does not take care of failures. It's too simplistic to believe that a 51% majority is a good approximation for a consensus value. Nevertheless, it is one solution that gives us an understanding of the problem that we are trying to solve. Now, one of the things that we need to answer before we move ahead and take a look at different types of consensus algorithms or mechanisms is that specifically within the context of blockchains, why do we need consensus? Now, one of the things we know is that blockchain is a distributed, decentralized network that provides immutability, privacy, security, and transparency. These four features are something that are the reason why blockchains exist. And blockchains don't have a central authority to validate and verify all of the interactions or transactions that happen on the blockchain, and yet every transaction that reaches and gets to become a part of the blockchain is considered secured and verified. This is only possible because of the consensus protocol that's available in the blockchains. A consensus algorithm or a protocol, as stated earlier, is a procedure through which all peers get to a common agreement. And blockchain networks establish trust between unknown nodes or unknown components in a distributed computing environment. So these are the two tenets based on which a consensus algorithm has to be built. Essentially, the consensus protocol has to make sure that every new block that we add on the blockchain is the only version or the only one that is the actual source of truth about all the transactions that have to form the part of the blockchain. And apart from the veracity of the block, we have to also ensure that the sequence of the transactions that form a part of a block are the same for everyone or same for every node or the component that's there in the blockchain. The blockchain consensus protocol consists of some specific objectives like coming to an agreement, collaboration and cooperation, equal rights to every node, and a mandatory participation of each node in the consensus process. Thus, a consensus algorithm essentially aims to find a common agreement that is a win for the entire network, or that is in the interest of the entire network. Some of the specific consensus algorithms that we're going to look at are proof of work, which we will dedicate an entire session to. But the one that we want to study first off is called the Raft consensus. And the reason why we want to study Raft first is because it gives us an idea of how consensus and some of its related problems were addressed prior to mechanisms like blockchain's proof of work or some of the newer consensus mechanisms that are currently being used. Now, Raft states that each node in a replicated state machine or a server environment can stay in one of the three states. This is the basic tenet or the basic sort of a proposition of the Raft consensus mechanism. And any node could be either a leader or a candidate or a follower, depending on a very, very specific set of steps that allow us to identify these three states for a particular node. Now, before we jump into the specifics of how Raft consensus works, let us try to understand what is it that we try to address with something called or some mechanism that is like the Raft consensus. So it is number one, a distributed consensus algorithm, and it's designed to be easily understood. It's not a very complex algorithm to follow. It solves the problem of getting multiple servers to agree on a shared state, even in the case of failures. Now, what one needs to understand is Raft is able to address the problem of reaching a consensus when a particular node fails in the entire set of nodes that are working together in a server cluster. What it doesn't address is if that node does not fail but starts to behave adversarially. What that means is that the node starts to give out conflicting information or starts to work against the network, which is uh, called Byzantine failure. So Raft is built for an environment where nodes work honestly or fail technically. It is called what's defined as a crash fault tolerant consensus mechanism. So a node can crash and be offline, but the entire system continues to work because it's tolerant to crashes. Now this is something important to understand because in public blockchain environments this may not be enough as a consensus mechanism, which is why Raft is not suitable for public blockchains. But that's a conversation that we will continue to have when we talk about Byzantine fault tolerance. Before that, let's try to jump into what we mean by Raft and how it works. So the basic proposition of Raft consensus mechanism is that it works by electing a leader in the cluster. So you've got different nodes that are working together in a cluster, and one of them is to be elected as a leader. This leader is responsible for accepting client requests, which could be requests for reading the state of the ledger, which could be a request for updating the state of the ledger, and it also manages the replication of that state. Now what we mean by replication is copying of a certain data from one ledger instance to all of the others. So it takes care of, number one, getting requests from a specific client, and then number two, managing that replication that needs to happen. So if we try to understand how Raft actually does that, the problem is three-stepped, or there are three phases to the problem. Number one, leader election. So one node which is taking care of all of what the leader is supposed to do does not stay leader for all the time. An election has to happen after a certain phase or a certain time, and a new leader has to be elected in case of either failure of the existing one or some other situations. The next is log replication or replication of data. So the responsibility of the leader is that it needs to keep a sort of a track or audit of all the servers in synchronization through what's called replication. Replication is copying of data everywhere. And then what needs to happen is that it's the leader's responsibility that the safety of the log is retained. No component of the network keeps its own log or has an additional entry in the log that others do not know about. So if we look at Raft consensus from a definition standpoint, you've got three components. One is the leader, which we've talked about. The other is the followers. So the followers are these other parts of the system that have to sync up their copy of the data with the leader, and that has to happen periodically as time progresses. When the leader server goes down due to whatever reason, then someone else or some other part of or component of the system has to contest an election and then become the leader itself. Now this election or this contest is a sort of the interesting part of Raft, where at the time of either the leader going offline or not being available due to whatever reason, certain followers can nominate themselves to become the leaders, and then just like normal elections, a server can ask for others to vote, and a certain candidate can be selected based on their requested vote counts, and they jump from candidate to an actual leader and take up the responsibilities of the leader. So at a very high level, this is the sequence of steps that happen during Raft consensus. Leader is the one that's taking care of synchronization of data and requests that come in from the client. Followers are the ones that are following the leader, synchronization of their state with the leader state, and then as a part of maintenance of this leader follower decentralization, an election happens once leader is no longer able to function, and a certain set of followers can become candidates to be selected as leaders. One thing that we need to understand is, as Raft operates, it divides the time of operations into what's called terms, and a term is essentially the amount of time a leader stays to be the leader. So it's the time between one election and the next one. If a candidate wins the election, it remains the leader for the rest of the term, and if there is a vote split, then the term ends without a leader and re-elections have to happen. If one server's current term is smaller than the other, then it updates its current term to a larger value. If a candidate discovers that its term is out of date, then it immediately reverts to the follower state. And Raft makes use of two procedure calls to carry out its basic operations. First is request votes, which is what candidates send during elections to all of the other followers, and then append entries, which is essentially what the leader sends while it's replicating log entries and synchronizing the entire network. A certain detail to the leader election is that the leader periodically sends what's called a heartbeat to its followers to maintain its authority. A leader election is triggered whenever a follower times out after waiting for an heartbeat from the leader, and if enough followers time out, if enough followers do not receive the heartbeat, it's assumed that the leader has essentially crashed or is offline, and then an election is supposed to happen. One of the things we'll do is we'll look at a practical implementation of the Raft protocol through a system called Apache Ratis. So Apache Ratis is an open source Java implementation of the Raft consensus protocol. But before we do that, one thing that I would encourage you to do is to go to raft.github.io. It has an interesting visualization of the Raft protocol. Let me refresh this page to show you how it works. So it's showing you 5 different servers. One of the servers is going to be elected the leader, and the rest of them are going to be followers. And the table that you have on the right hand side essentially is going to show you the log replication. So right now S1 has been elected the leader. It's sending out these heartbeats to all the followers, and it's getting acknowledgement of those heartbeats, and each servers from S2 through S5 is updating its logs. We can also configure this and speed up the process just by adjusting these time variables that they provided, but it's essentially an interesting sort of a visualization that can give you an idea of typically how Raft protocol operates. Now, Raft is something that's used not just in blockchains, but in a lot of other systems, and Hyperledger, which happens to be a very popular private blockchain platform, uses Raft as its default consensus mechanism. The next step is to demonstrate how a client can work with the consensus network that we have created using Apache Ratis. So the first thing we ensure is that our server is running. It's currently configured with 3 different nodes, and it's constantly running elections and voting and all of the steps that a typical Raft consensus system executes. On the client side, we have to ensure that there is an ability to execute the core proposition, which is to read and write files, and not going in depth on how that happens. They have supplied a specific client script that allows us to create clients, and it's a part of the actual shipment, the actual release code. All you have to do is, just like setting up parameters earlier where we declare the binary directory, the same binary directory has the client.sh file, which executes with a set of parameters. The first one is the file store load generator, and then it accepts the size of the file, the number of files that could be written and read, the storage, which is a temporary location, and then it looks at the peers that we have set up. So all of these peers are server peers that it's supposed to connect with. So we'll try to execute it. As you can see, there are going to be a number of errors, primarily because it connects with peers that are not leaders and are no longer able to write. So it's moving too quickly. If I pause it or stop it, you'll be able to see the exact set of steps that were executed as a part of the file read and write, where it was trying to set up a channel, create a connection, and then look at the client leader to be able to write the file. Again, this is a very specific use case, not going in depth of how it's to be used. If we again go back to Apache Ratis, if we go back to the Apache Ratis page, we're going to find how it can be used in a project of our own using Maven dependencies. It is a recommendation that we understand how Maven works as a build system for Java, just to be able to manage different kinds of dependencies. What we've just done is executed this file store example as a way of how Apache Ratis as a reference implementation of the Raft protocol is to be used. There are simpler use cases one can implement. We'll not get into those right away, but it's something that's recommended if we are building out an entirely new consensus system, which is going to be built on Raft. One of the things that is a part of implementing Raft as a consensus mechanism is the ability to customize it. It is out of scope of this discussion, but it's something that one can be encouraged to explore. So with that, we have this one demonstration of the Raft protocol. It is used very frequently in private blockchains. It is performance optimal, and it helps setting up systems that can handle enterprise or private blockchain concerns. We will take a look at this in detail when we try to understand how a blockchain platform called Hyperledger works. Hyperledger has Raft consensus by default. One of the things that we have to understand around Raft consensus is that it is only crash fault tolerant. It is not Byzantine fault tolerant, which means as long as there are a couple of nodes that are working, the system by and large is going to continue to work even if one specific node is not able to function, is not able to connect, or goes down. This is an important distinction to make because Raft is primarily not used in public blockchains because of its weak tolerance and the weak nature of the tolerance that it provides. We will take a look at proof of work and Byzantine fault tolerance as the next consensus mechanism. We will get to how a very simple proof of work is executed, which is a part of that same consensus mechanism through again a demonstration that we will execute through Java. So the proof of work demonstration is much simpler than Apache Ratis, which is a complete project in itself. What we have here is a very simple set of Java classes that are going to demonstrate how proof of work works. So this is a set of 3 classes. It's already been compiled, so I've removed the compiled classes. I want to demonstrate how we will compile and then eventually run this. Before that, just quickly jumping into the code to demonstrate what we'll attempt to do. We will supply some command line parameters to this Java program, and then we will try to essentially execute a loop that's going to constantly calculate SHA-256 output, and then we will try to apply a level of difficulty to this integration. So the concept of difficulty is again something that we will discuss in detail. It would be enough, or it would suffice to say that difficulty essentially represents how strong the proof needs to be, and the essential proof of work is going to be in this loop, which is going to demonstrate that a certain number of iterations were performed, each one of them executing this calculation of SHA-256 hash, and then checking whether this hash satisfied the level of difficulty that was set out for it. If you can see, if you're familiar with Java, you'll see that the moment this hash test succeeds, we are going to break out of the loop. And if we don't, we will keep incrementing what's called the knowns and keep looping through our problem. So to be able to execute it, there are some simple steps to follow, and we will capture these steps as command parameters. So the first thing to do is to compile the Java programs, the Java classes that we have. The compiler command is javac. So we have the src folder under which we have our source files. We've got proof of work, we have compiled that. We've got proof of work verifier, successfully compiled, and then utils. So now if I go back to my directory, I'll see the new classes that have been compiled as .class files. Now to be able to execute it, I already have the command built out. I need a couple of command line parameters, and I'll just demonstrate what those are. So to be able to execute the proof of work, I will have to use the executable Java supplying the proof of work class name, followed by difficulty, and then there are some alphanumeric strings that I'm supplying. If I look at the code, I'll be able to tell what each one of them means. So if you look at the first parameter, that's the difficulty level. If you look at the second one, it's got what's called the previous block, and we did some analysis of how blocks are structured and what previous block and Merkle root means, and we're basically supplying them as parameters that have been pre-calculated to demonstrate our problem. And then the third parameter is the timestamp. Timestamp is something that we will use as something that we will add to each block as we iterate through them. So once we've identified all the parameters we need, we can simply execute this program with those parameters. Now what you'll notice is we executed and found out so many hashes, and then finally arrived at the hash that satisfied our difficulty level. The level of difficulty that we had satisfied was in the first parameter, which is 0, 0, 0, 0, 0. What this difficulty level means is that we are looking for a hash that is preceded by these many zeros. In terms of blockchains, we can say the level of difficulty here is 5. I could just customize this a bit and add one more difficulty level, and what I'll find is it's going to take me a couple of times more the amount of time that I took in the earlier execution. As you can see, it's constantly checking for hashes. It might take a very long time before we are able to get to the hash with difficulty level 6. So although I paused the video, it took a good amount of 5 minutes before the block was mined, and the knowns needed to be this long and the block hash needed to be this one. The next step that we can execute is to verify and then check whether that blind block is the current format, and to do that we will execute another program, Java's proof of work verifier. So I've captured the command here. It's going to verify a certain hash and a certain Merkle root, whether that hash is a part of the Merkle root. We just executed. Have to be in the src folder. So what they find that it's a valid block. If we just look at the code of the verifier, we'll see that it accepts the previous block in the Merkle root and just checks whether the hash that we calculate, whether it's with the amount of difficulty, whether it's equal with the amount of difficulty supplied to the hash that we calculated after the Merkle root was arrived at. So both of these are a part of the README file with this code, and you can look at the GitHub link from where you can download it. It's a very simple two-step program that lets you calculate proof of work and verify proof of work. Both of these commands can be used as it is. If we are intending to change some parameters, just make sure that they are valid hashes. So with that, we come to one step forward in our demonstration of how proof of work works towards building a proof of work consensus mechanism. We have not seen it end to end because there obviously needs to be a blockchain, a block, and a transaction to uh, kind of demonstrate how this specific proof of work scheme is going to be used. And that is something that we will do towards the end of these sessions, where we'll build a complete end-to-end blockchain. So we've seen some of the other blockchain consensus mechanisms like proof of stake, and we've discussed them. We will demonstrate them in some of the coming sessions. Proof of elapsed time, which is something that's interesting. We will look at how that can be implemented as a part of a demonstration. With that, we've come to the end of a very high level treatment of the consensus protocol and what are some of the consensus mechanisms available for us. Hope this was useful to you. It was again at a very high level. There'll be details to this that we will get into as we go along. Thank you.